In this video, we discuss learning outcome number 6 for lesson 10.2, which is about residual plots. My hope is that after watching this video, you'll be able to examine residual plots to determine if a regression equation is a good model and explain what the residual plots suggest about the original paired data. We're going to define the term residual plot, talk about how you can create a residual plot. Usually you're using technology to do this rather than doing it by hand. And then I want you to be able to describe how we can use a residual plot to analyze correlation and regression results. So first, let's start with the definition. A residual plot is a scatter plot, but instead of graphing the XY pairs, each Y coordinate has been replaced by the residual Y minus Y hat. Or in other words, the residual plot is a graph of the ordered pairs X and Y minus Y hat. This turns out to be a helpful tool for checking the formal requirements necessary for making inferences about correlation and regression. If you want to construct a residual plot, first you're just going to draw a horizontal line representing a residual of 0. So it's just Y equals 0. And then you want to plot those ordered pairs X and Y minus Y hat throughout the XY plane. So to give you a concrete example, let's look at that chocolate consumption and Nobel laureate rate data set. Remember, we have chocolate consumption in kilograms per capita in different countries. And then we have a Nobel laureate rate. This is a number of Nobel laureates per 10 million people in that country over the history of the time that the Nobel Prize has been awarded. And so it looks like we have a particular country with a chocolate consumption of 4.5 kilograms per capita. And in that country, there are 5.5 Nobel laureates per 10 million people. In another country, they consume 10.2 kilograms of chocolate per capita, and they have 24.3 Nobel laureates per 10 million people, and so on. We've got 23 ordered pairs representing 23 different countries. Now, if we look at the graph of this, the graph of these ordered pairs, we have this scatter plot. The red dots correspond to particular ordered pairs over here. For example, this one here, we've got a chocolate consumption near 12 and a Nobel rate near 31 or 32. If we go over here to our data set, I bet we can find it. Here we see that when the chocolate consumption is 11.9 kilograms per capita in one particular country, the rate of Nobel laureates that they have is 31.5 Nobel laureates per 10 million people. And so that ordered pair 11.9, 31.5 is represented by that data point. Now this line is the equation, or excuse me, this line is the regression line. It's not the equation of the regression line, it's the actual regression line. And that is given by the regression equation, and that was discussed, I believe, in your textbook, the exact regression equation for the Nobel rate, or the chocolate consumption versus Nobel rate data. I think I may have mentioned it a couple of times in the videos as well, although we did not derive it. We derived a different regression line instead, or a different equation of a regression line instead. But if you take this and for each data point, you compute a residual. So you take the Y value and you subtract the corresponding Y hat value. And you do that for this point and for this point and for this point and for this point. Remember how this works. I'm trying to get my little annotation box up. So the residual right here is that distance from there to there. All of these above the line have positive residuals because the Y value minus the Y hat value is going to be positive. This is the largest positive residual right there. And then all of these down here, the Y hat minus, or the Y minus Y hat value will be negative because they're below the line. But the lengths of these line segments, the directed lengths of the line segments, where the line segments that are above the line are, we find the distance and then we count that distance as positive, and then the line segments below the line, we find the distance and then we count that distance as negative. Those are the residuals that correspond to our regression equation and this particular data set. Now, if we take those residuals and we graph them, we get a graph that looks like this. This is a residual plot corresponding to this scatter plot and this regression line that we have here. Okay, just for example, let's look at a particular x value. When x is 6.4, according to the regression equation associated with that consumption of chocolate per versus Nobel rate data, we had y hat equals negative 3.37 plus 2.49 times x. If x is equal to 6.4, the regression equation predicts that our y value would be approximately equal to negative 3.37 plus 2.49 times our x value, which is 6.4. And that turns out to be about 12.566. It's approximately there. Here's 6.4 approximately, and the y value when x equals 6.4 is about 12.5. That's what that says. But if we look at our original data, we had that table with 23 ordered pairs on it. One of the ordered pairs on that table is x equals 6.4, y equals 31.9. So there is a particular country in our data set that has a chocolate consumption rate of 6.4 kilograms per capita, and they have 31.9 Nobel laureates per 10 million people in their country. So when x is actually equal to 6.4, there is an actual country that has a y value of 31.9 Nobel laureates per 10 million people. And that corresponds to that value right there. The difference between the y value up here and the y value on the line, that's our residual. So the residual is 31.9 minus 12.566, which is 19.334. Now on our graph over here, that corresponds to this point. When x equals approximately 6.4, the residual that corresponds to this point, or the distance from here to here, is plotted right here. And the distance from that zero line is about 19.334, which is consistent with our picture. You do that for all 23 ordered pairs. For every y value, you find the difference between the y value and the y value predicted by the line, and then you plot that residual. That little distance gets plotted down here. So the distance from here to here gets plotted from here to here. And this little distance from here to here gets plotted from here to here. And the distance from here to there is that distance. And the distance from there way down to there is the distance from there way down to there. So we're using this y equals 0 as sort of our center line. It's almost as if we took this and we just sort of turned everything sideways and thought of this as our new x-axis, and then looked at the distance between each of these points. Well, the distance between each of those points and the y value here, but we're not actually going at a right angle. We're going at an angle that's going straight down in order to find those residuals. That's how we got this plot right here. Now, of course, we use technology to compute all of those values, and that would be relatively simple to do. Once you have that y hat, you have your regression equation. You could plug in all of the x values that you have to the regression equation to find the y hats associated with every x value in your data set. And then you could take the difference between the actual y value that was observed, so an actual rate of Nobel laureates in a particular country, and the predicted rate of Nobel laureates in a particular country, y hat. So you could subtract y hat from y, you could find a bunch of residuals and then plot those. This is what the plot would look like. Now, again, the reason we do this is because it's a helpful tool for checking the requirements necessary for making inferences about correlation and regression. We talked about these requirements for finding the equation of a regression line. We said that if you have a set of ordered pairs, you can always find b sub 0 and b sub 1, which means you can always find an equation for a regression line. But just because you can find one doesn't mean you ought to. We really only want to find the equation of a regression line and use the equation of a regression line as an estimate for the true population regression line if the following requirements are met. First, our sample of paired data has to be a random sample of quantitative data. And then we said the next two requirements need to be satisfied. Visual examination of the scatter plot should show that the points are approximately in a straight line pattern, and any outliers that are known to be errors should be removed. And we said that those last two requirements were really our very informal way of trying to satisfy these formal requirements. We have these following three formal requirements, for regression analysis. And it turns out that this residual plot that we've just examined, that we've just looked at, is an excellent way to check these formal requirements. And what's really nice about it is that it's a visual way of checking these requirements. And it may be even better than trying to check requirements 2 and 3, as we've done here. Sometimes all of this seems very subjective. It's a little bit less subjective when you use the residual plot to check these requirements. So remember, these are the formal requirements that we're trying to confirm or trying to verify with requirements 2 and 3. For each fixed value of x, we want the corresponding values of y to have a normal distribution. And then for different fixed values of x, we want the distributions of the corresponding y values to have the same standard deviation. Now we say that this is violated if the scatter plot shows points very close to the regression line in one part of the graph, or one part of the scatter plot, while another portion of the scatter plot shows that the points are very far away from the regression line. In that case, we might assume that the y values don't all have the same standard deviation for different x values. And our last requirement is to check that for different fixed values of x, the distributions of the y values have means that lie along the same straight line. So if we want to analyze a residual plot, this is what we will look for, and this is what the residual plot will tell us about those formal requirements that I just mentioned. In order for those requirements to be met, the residual plot should not have any obvious pattern. If there is an obvious pattern, there may be some other pattern in the scatter plot. If the residual plot doesn't have an obvious pattern, that confirms that the scatter plot of the original data have that straight line pattern that we are looking for or expecting, as opposed to some other pattern. Second, our residual plot should not become much wider or much thinner when viewed from left to right. In other words, the residuals should not be getting farther from that 0 line or closer to that 0 line as you go from left to right. This confirms the requirement that for different x values, the distributions of the corresponding y values have the same standard deviation. So if we start to see a gap that's widening as you go from left to right, or a gap that's closing as you go from left to right, then we might say maybe those y values have a standard deviation that's changing as the x values change, and we don't want that. Okay, so here are 3 examples. We've got a residual plot. This turns out to suggest that the regression equation, is a good model. We can see why there's no obvious pattern to these residuals. And also the residual plot doesn't become wider or thinner as you move from left to right. The residuals seem to be sort of randomly distributed. We've got a small positive residual here, slightly larger negative residual, a large negative residual, a much larger positive residual. It seems random, and that's a good thing. That means the regression equation is probably a good model. Now here's an example of one in which the regression equation may not be a good model. This graph itself suggests that the regression equation is not a good model. You might be saying, why? Well, look at the residuals. The residuals start negative, and then they become very positive, and then they go down and they go negative again. And it's sort of like this pattern. It looks like a wave pattern. Since there's an obvious pattern there, that suggests that the original scatter plot will probably not follow a straight line pattern as required. So if you're looking at your scatter plot and you can't tell, you're like, it kind of looks like a straight line, but maybe not. If you graph the residual and it looks something like this, the residual plot, then that tells you that, at least for our purposes, if I have a distinct pattern in the residual plot, then I'll say, I don't think that that is really close enough to a straight line pattern in the original scatter plot. Now here's another residual plot. Notice that we have a 0 residual. That's nice. The model is excellent at predicting. And then we have a tiny little bit of an error. It's positive, a tiny little bit of an error that's negative. Then the model is spot on again, the model giving us exactly the Y value that we see in our data set. But then look what happens. That error gets larger and larger and larger and larger and larger and larger. So as you move from left to right, as the X values increase, the error gets to be larger and larger and larger. And error, again, is another name for residual. The error is sort of the absolute value of the residual, if you will, or the, maybe, well, just depends on who defines it. Yeah, you can see that the error is getting grossly worse. It's getting much worse as the X values get larger. That suggests that the requirement of equal standard deviations for every Y value, or for every different X value, the standard deviations for the Y values are supposed to be the same. This suggests the standard deviations for the Y values aren't the same. Seems like there's more deviation as you go farther to the right. So those are examples of residual plots, and hopefully you understand now how they can help you determine whether your regression equation is a good model, as long as there is not a pattern and you don't see the residuals getting farther and farther from that 0 line like this, or closer and closer to that 0 line, like as if we were going the other way. As long as you don't see that, then you know that the standard deviations of your Y values given different X values are probably the same. And as long as you don't see a pattern in the residual plot itself, you know that the original scatter plot is close enough to a straight line for our purposes. And if both of those are satisfied, that means this residual plot implies or suggests that the regression equation is an appropriate model. That means those 3 requirements, those formal requirements that we were attempting to check with requirements 2 and 3 from our shortlist, can be confirmed using a residual plot in this way. I hope that helps you. That is the end of our last lesson for statistics. I hope you enjoyed the video series. I enjoyed having you in class. Don't hesitate to reach out if you need anything. Good luck on your finals. I'm rooting for you. See you later.